Yo, welcome back. All right, so we're sticking with continuity. There's one thing that I actually wanted to emphasize that I forgot in the last notes piece was a little of how things play out. All right, so for example, when you're doing a problem, right, how are you going to know you're going to get a hole? Well, we talked about it, right? The limit would the two-sided limit would exist, and it wouldn't equal the functional value. But more than that, if you directly substitute and you get 0 divided by 0, right? So you substitute a value in like 7 and you get 0 in the numerator and the denominator, that's going to tell you that you have a hole, all right? And we'll talk more about that later. So go back to your notes and just add that in there, all right? That this tells us we have a hole, all right? Similar here, the only difference is this would be a piecewise function where you'd have your hole for the one branch, you plug into the one branch and you get that, and then there'll be another piece that just says the function is this value somewhere else. So that's not too exciting. Um, so that's that. Now, as opposed to this is pretty clear cut. The has nothing to do with the functional value or what you plug in. It has everything to do with the one-sided limits being different numbers. But then this, there's also like a heads up on this guy on the essential. So sometimes when you plug into a function, right, we've seen this, you don't get 0 over 0, but you get not 0 over 0, right? So I always write number over 0, but it's probably not the best because 0 is a number. So maybe I should emphasize that you get not 0 over 0. So when you get not 0 over 0, that is going to tell you that you have a vertical asymptote. All right. So 0 over 0 when you plug in, you're going to get a hole at that value. Not 0 over 0 when you plug in, you're going to get a vertical asymptote. That's true 99.987% of the time. All right, so moving on. So we finished up continuity. There's some theorems that we want to talk about. They're not the most exciting, and I don't plan on proving them, but I should state them. All right. So take a look at that first theorem that we have up there. It basically says if you have two continuous functions f and g, then if you do addition, subtraction, multiplication, or division, the result is also going to be continuous. So in other words, if f and g are continuous, then so is the sum of f plus g. All right, so in other words, the sum of two continuous functions is continuous, or the difference of two continuous functions is continuous, or the product of two continuous functions is continuous, or the quotient of two continuous functions is continuous, but you do have to have that little added thing here, provided that the bottom isn't equal to 0 at the point that you're interested in, right? And this theorem actually generalizes to more than two functions. So nothing too exciting there. It kind of comes as a result of the limit properties themselves. So this shouldn't seem too bananas to you. All right. Let's take a look at the next one. And this is kind of interesting because depending on the textbook you pick up, depends on how they want to go about this. So I'll just kind of read it. All right. And I got both of these from textbooks. If the function g is continuous at x equals c and the function f is continuous at x equals g of c, then we say that the composition is also continuous, right? You can kind of cloud that up and say basically if you have two continuous functions, then the composition will be continuous. Now that's not 100% true. That's only true if as you're working your way from the inside out, if the next immediate function is continuous at the value of that limit. All right. So more generally, we actually can write, and this is, I kind of like this. If you know the limit of g of x goes to c is some number L, so in other words, it exists and it's L, and you know f happens to be continuous at that number, that's kind of important. Well, then you can say the limit of f of g of x, right? That's a composition, is equal to f of the limit of g of x as x goes to c. Notice that's why when you get L for that limit, the function has to be defined there. And then that would equal f of L. You know, the whole confusing takeaway of this is basically a function, or I should say this, a limit can be pushed through a function. So think about how we took this limit as x went to c and we kind of pushed it through f. You can do that provided that the function is continuous at that inside limit. All right. Again, I'm not going to prove that one to you. We're just going to kind of go with it. So let's actually look at an example of how we might want to do that problem. So we'll do it. We'll do it with this next one right here. All right. So let's take a look at the limit as x goes to infinity of cosine of all of that stuff right there. All right. How would I do that? Well, you can't really directly substitute infinity, right? Because you're going to get like an infinity over infinity, and believe it or not, that's also an indeterminate form. So, what the heck do you do here? Well, the first thing you can do is you can go ahead and you can take this limit and you can push it through the cosine function. All right, so that's what I'm going to go ahead and do. So I'm going to rewrite this as the cosine of the limit as x goes to positive infinity. And as long as cosine is defined at the value of this limit inside here, then I'm going to be good to go. All right, so now how would I do this limit? Well, this is now review from what you were doing earlier in class, right? This is limit to infinity. We're going to want to use an end behavior model, right? So remember how you do the end behavior model for a rational function. You look at the term that dominates in the numerator and you divide that by the term that dominates in the denominator. You have to take the signs. So I can rewrite that internal limit there as cosine of limit as x goes to positive infinity of pi x squared over negative x squared. Okay, and that's the end behavior model for that. And I chose to do that because it's a limit to infinity. So now obviously the x squareds are going to cross out, right? Those like factors are just going to be 1. So you end up getting a limit of negative pi as x goes to infinity. And so then that means you would just get the cosine of negative pi. And you can do that, right? If I'm thinking about the unit circle, right, pi is here. If I go the other way, if I rotate clockwise, right, that would be negative pi, right? X value, y value in the unit circle, the x value is -1, so I end up getting -1. So, not the most exciting problem in the world. Just see an example of how we can rewrite a limit expression by kind of pushing the limit through a function, provided that the function is continuous at that internal limit and cosine is continuous at negative pi. All right, so nothing crazy. 3 may be the most exciting. Maybe it's not, but I think it is. Right? If a function's a polynomial, then it's continuous. That basically means you have the right in this class, whenever you want, to say that polynomials are continuous everywhere, because they are, right? I mean, just think about it. Lines, you can trace them without lifting up your pen. That's a degree 1 polynomial. Parabolas, you can trace them without picking up your pen. Degree 2 polynomial. Degree 3 polynomial, right? There are no holes or breaks in polynomial functions. They are continuous everywhere, and we're going to want to have that in our little arsenal of things to say when we're trying to justify stuff. So you are allowed to say that. You don't have to prove it to me. The proof is actually pretty simple, and it goes back to that polynomial mold, right? That general polynomial. And we basically kind of already proved it when we showed that the limit of f of x went to c of that polynomial actually equaled f of c. So believe it or not, you already have the proof of why polynomials are continuous at every point c. All right, moving on. Let's do a cool little problem here, and then we'll take a break. All right, so take a look at this guy. Given the graph of f, for each value, a equals 0, a equals 1, a equals 5, determine whether or not f is continuous at these values. And in each case, use the definition of continuity to justify your answer, just like I said they were going to do, right? So remember, what is the definition of continuity? The definition of continuity is that if you look at the two-sided limit as x goes to some value, we've been using c, but you can use anything. You know what? I'll switch it up to a. So the limit of f of x goes to a from both sides. If that, in fact, is equal to f of a, then we're continuous. If it's not, we figure out why it's not, and that determines what type of discontinuity we have. All right, so let's do this. So let's start with a equals 0. So if I go with a equals 0 here, right, I would say, hey, the limit of f of x as x goes to 0 from both sides does, my little question mark equal, does that equal f of 0, right? You can look at the graph here. As x goes to 0 from both sides, what do you know about that limit? Well, it's not going to exist, right? But why is it going to exist? Well, because the limit of f of x as x goes to 0 from the left, that's going to be 1. And the limit of f of x as x goes to 0 from the right, that's going to be 2. So this right here tells you there's a jump, okay? So this would tell us right here that we have a jump discontinuity at x equals 0, okay? So we're not continuous in 0. All right, so let's look at that next value now that they wanted, a equals 1. So again, start with the definition of continuity. I'm going to look at the limit of f of x as x goes to 1 from both sides, and I'm going to determine, are you equal to f of 1? Well, here's 1 right here. So as x goes to 1 from both sides, my functional values, my limiting values, my limit buggies are approaching 4. My functional values are approaching 4. I don't know why I said I'm sorry. All right, it's early. So this limit would exist, and this limit would be 4, but it's not equal to the functional value, right? F of 1, that's the dot. So that's 3. So that's no good. So now what happens when the two-sided limit exists, happens to be 4, but it's not equal to the functional value, right? Well, that is the picture painted for a removable discontinuity, exactly what you're seeing here, right? So therefore, there is a removable discontinuity at x equals 1. Okay, so again, definition of continuity, paint the picture. Definition of continuity, paint the picture. Let's do the last one, a equals 5. So for a equals 5, again, definition of continuity, limit of f of x, as x goes to 5 from both sides, does that equal f of 5? Well, 5 is right here. So as x goes to 5 from both the left and the right, it looks like my functional values, right, my little functional buggies, they're approaching -2. What would f of 5 be? Well, that would be this here. You don't have to have a big dot there, right, for you to do the functional value. Functional value is that y value right there. So that's -2. And you're like, oh yeah, what does that mean? Two-sided limit actually equal to the functional values, and then that means, by definition, we're continuous at 5. So therefore, f is continuous at the internal point x equals 5. Okay? Solid little question there. All right, we'll take a break. We'll come back and we'll do one that's a bit more solid.